let's continue. Good. It will be like this. It will be hopefully no more than 5+ minutes towards the end of first part of the talk, and then I switch to actual slides for the second part of the talk. And again, questions are more than welcome. So here's where I want to finish, just not with everything I wanted to show, but at least with some portion of it. So superconductivity and strong coupling for electron-phonon system when coupling constant that determines essentially d sigma over d omega is large, while the coupling that determines vortex corrections and correction to coming from Landau damping is governed by parameter which is small. Tc is Debye frequency for any case, function of the coupling constant lambda. There is no lambda E in the expression for Tc. There is no expression for Fermi energy anywhere in the gap equation. At weak coupling, we know the result. Tc is some number times Debye frequency times this exponent. The question is what happens at strong coupling. And as I mentioned towards the end of my talk, in 1975, long time ago, Allen and Dines working, essentially looking at experimental data, phenomenologically argued that Tc can be larger than Debye frequency, and in fact scales the square root of the coupling constant. At that time, there was a lot of discussions, which in fact continue today, whether it's at least theoretically possible to make Tc larger than Debye frequency, or Debye frequency is ultimate cutoff for Tc. This story, the answer is not settled, because in fact what I will be telling you is what's called mean field Tc, the one that doesn't include phase fluctuations. And let's at least look at this one. With phase fluctuations, actually Tc can be and should be smaller. So anyway, if we recall that coupling constant is g over Debye frequency squared, then substituting square root of this quantity, you see omega d cancels out, and you get temperature that's proportional to g, which actually means that it looks that you write down gap equation, and you can strike out Debye frequency, make it 0. You cannot, because remember, this parameter lambda e also contains Debye frequency in denominator. So technically, you cannot do this. But if you look at the gap equation, it's not critical. It doesn't depend on this parameter lambda e. And therefore, knowing that the result is just g, meaning that I can forget about Debye frequency and assume that it's like it's 0. This is just for accuracy, just how to do it accurately. Let's look at this. This is the gap equation that we obtained, the Cele-Ashberg gap equation, the one for Tc linearized for very small value of delta, so there is no delta in denominator, and I eliminated Debye frequency here. So it's just like I put it 0. There is only one scale here, g. But we have interesting story. We have divergence here. Look, if I need to sum over all Matsubara frequencies, and when the one over which I sum equal to the external one, I get 0 in denominator. I actually get square of 0 in denominator, which is bad thing, divergence. However, you look at the numerator of the gap equation, and here is the difference between weak coupling and strong coupling. At weak coupling, there is only one term like this. At strong coupling, there is additional term coming from self-energy. And then look carefully. I assume that we all will see this. When omega prime is equal to omega, numerator is 0. Right? And even more, even if I keep omega d in denominator, numerator will still be 0 when omega prime equal to omega, which means I can safely limit when Debye frequency goes to 0, and divergence of denominator is completely compensated by, 0 of denominator is completely compensated by 0 of numerator. So this problem doesn't have singularity. And once you realize that it doesn't have singularity, the rest is just obvious. And you may ask physically what it means. And who heard about Anderson's theorem for superconductors? Some of you did. Anderson's theory of superconductors basically tells you that non-magnetic impurity don't affect Tc. And it's exactly the same story. Because what is this? Scattering at 0 frequency transfer. And remember, there is no dependence on momentum, which means that I scatter fermions by any momentum transfer and zero frequency transfer. I just do scatter-like impurities. So in this respect, electron-phonon interaction is the limit when transfer frequency is zero, acts like impurity scattering. And just like conventional non-magnetic impurities cancel out in the gap equations, the same happens with this contribution at zero bosonic frequency. It just cancels out in the gap equation. Cancels out means that I keep the bi-frequency here. Term with omega prime equal to omega is zero because of numerator, so I can just get rid of this term. The rest contains at least 2 pi t square in denominator because the difference between these two frequencies is 2 pi t. So long story short, no divergence here. You solve this equation. You can do this numerically, of course. It's trivial. And you get an answer number times g. Yes, Allen and Dynes were right. You get Tc, which scales as interaction. This solution. There is some interesting number. We'll discuss it a little bit. Very good. At this stage, I ask the question to which I try to answer later. How can it possibly be? We consider situation when we have interaction mediated by by Einstein phonon, and we know from the beginning that yes, this interaction is attractive, but at frequencies lower than the bi-frequency, and repulsive at frequencies larger than the bi-frequency. Yet, it turns out that temperature that I get from the solution is finite when the bi-frequency is set to zero. So apparently I get superconductivity out of completely repulsive part of the interaction. Let's take this as a note, and then discuss it towards the end of second part of, or second lecture, which will follow. At this stage, all I want to show you is one extra thing which is also important. I said divergences cancel out in the gap equation. You saw this, they do cancel out. But what about fermions? What about quasi-particle residue for fermions? Or quasi-particle normalization factor, Z? It doesn't show up in the gap equation, but it shows up as a property of a system. So you look at equation for Z, you look at this, if it's normal state, and delta is very small, and nothing cancels out, you get this contribution. So this means that self-energy diverges. You have real divergence. Moreover, you can say, wow, okay, it's finite frequency effect. Do it at zero frequency. Do instead of summation, do integration. You still get divergence, which means that for any frequency, self-energy is divergent. Theory has divergence. It's a very uncomfortable thing. Normally, it's better not to have this. Nevertheless, superconductivity is insensitive. So details, but superconductivity is insensitive to this divergence. Numerics. People did numerics, and Tc, as a function of the bi-frequency, as a function of the coupling constant lambda, should scale as square root of lambda. Look at this form. It's pretty much square root. We said that Tc should saturate at a finite value when the bi-frequency goes to zero, and the bi-frequency goes down means that the coupling constant goes up. So I will show you next plot as a function of the coupling constant and other numerics. And you see that Tc as a function of the coupling constant, yes, it saturates at some value, which in fact, this is 0.18 G. I didn't put numbers, this is 0.14. So not exactly the same, but the good accuracy is the same. Very good. I can continue with this, but let me stop because I want to tell you something funny about second part. Superconductivity develops a strong coupling. This is a conclusion from Eli Ashberg's theory of superconductivity, even in this very uncomfortable thing that self-energy diverges. In fact, I'll open a secret. You can do all calculations at zero temperature, assuming finite superconducting gap delta. Self-energy still will diverge. It's unavoidable. You get divergence. Superconducting saturates at a finite value when the bi-frequency vanishes. Let's take this as a note with big question mark. How can it be? Because we supposedly get it out of repulsive interaction. With this, let me do this. Oops, why the hell is going to this one? And I want to go to another talk. And I want to do slideshow and from the beginning. And I hope it will work. Let's see. Suppose Supposedly it works. Very good. So, second part of the presentation, superconductivity coming out of non-Fermi liquid in general. What it all means? The question is, first part was about electron-phonon interaction. Let's come down for a second and ask a general question. Are phonons always responsible for superconductivity? Well, in the materials known before 1986, the answer was pretty much yes. But as we all know, something happened in 1986. TC went up almost vertically. Nobel Prize came with a record velocity, much larger than Fermi velocity. And all these superconductors are phonon superconductors. And then something happens. It jumped. Does it mean that's non-phonon superconductivity? Actually, no. It just went up. Okay, few years, well, few means number of years passed. In fact, do you know what the correct number, correct year? 2006, not 2008. First paper was published in 2006. Nobody noticed it. For 2 years, there was zero information. And then splash. What is splash? Well, this is splash, right? Number of Nature and Science paper came to absolutely record. Very good. Few years later, wonderful superconductivity in twisted bilayer graphene, then in Bernard bilayer graphene. This is what Steven and Eris will be talking about, so I don't go. And I guess Paiva will also be talking about this part. So there are a number of other materials in which superconductivity has been detected, and lists keep growing. And the question, are these all phonon superconductors? In fact, I guess for any of these materials, there will be people in the community who will say yes, it's maybe phonon superconductivity. But every time there is a big question. Let me tell you, for example, first of all, is it the fact that TC went up vertically that important? It is, but to a certain extent. There's another discovery. There was discovery of MgB2, which is definitely phonon superconductor in 2001. It was discovered, and you see temperature is 40 Kelvin. It's larger than in lanthanum-based cuprates, larger than in most of iron-based superconductors. And it's pretty well established that this is phonon superconductor. The funny story about this material is that there were experiments done, I guess, in 70s, which stopped somewhere here. They were doing measurements, and then, boom, stopped and said, don't worry. And the second is that this material, normally you ask a question, particularly for experimentalists, you ask them how to make materials, etc. I was told by my friends that this material was available by mail for a large number of years. You can just order it and get it. Yeah?
Sorry, I don't want to defend all experimentalists, but there was a time when going below nitrogen temperature
yes.
was very expensive.
Yes. It was very expensive. Yeah, and no, nevertheless, it is as it is. So, yeah, so this is phonon superconductor, pretty high temperature. So, actually, by the way, referring to your talk and extending it a little bit, but you showed the data. Of course, highest TC, as we know, is in electron phonon superconductors, which is hydrogen sulfates and lanthanum and yttrium sulfates. What's relevant? The answer depends. I'm not standing here telling you ultimate answer. You ask someone else will give you different answer. But my take is that if you combine all these materials, then there will be argument why electron-phonon interaction is not the case. For example, in the case of iron-based superconductors, you do best case calculations for TC, electron-phonon systems. Somebody will have a question for me. How can it be electron-phonon superconductivity in the S-wave superconductivity in the presence of much larger Coulomb interaction? This was obtained even without looking at Coulomb interaction. Still get 1 Kelvin. Actually, TC is 60 Kelvin in good materials. So there is a big difference. And then we come to the issue that what is other choice? Another choice is electron-electron interaction, right? If we don't have external source, let's try to think internal source. And I'll give some of the slides here just to give you a hint. This is probably the best heavy fermion antiferromagnet in which you see nail temperature going down, supposed to go to 0 in what is called quantum critical point at 0 temperature where the order disappears. But around this point, you see superconductivity emerges. Less spectacular here, which is heavy fermion ferromagnet, but what I raise here, there is a second ferromagnetic transition which goes right through this point, less detected, but nevertheless, still superconductivity close to the point where, where ferromagnetism disappears. Cuprates, pnictides definitely have magnetism and possibly as a player for superconductivity, also pneumatic order. So there are some orders in electronic systems which exist very close to the point where superconductivity develops. Let's go to more recent time. In fact, this is one of the results which I guess Steven will show. Biased Bernard bilayer graphene in a displacement field produced by electric field. And you see superconductivity. Eris will also show this, I'm sure. You see superconductivity, nicely seen here as a reduction to 0 of resistance, but very close to the point where the system is about to develop order, and then let's not discuss what kind of order develops here. Very good. Now, if we play this game, then near every instability of electronic system, one can define low energy bosonic states. I mean collective excitations which condense on the other side of the transition. And ask a question, can it be that instead of phonons, which are soft excitations compared to electrons, we can consider effective interaction mediated by the soft bosonic modes, which has one difference with phonons. They belongs to electrons. They are collective modes of electrons. It's just electrons interacting by exchanging their own collective modes, which in fact means this. It's electron-electron interaction renormalized in particular channel. This renormalization produces you denominators, and denominators can be interpreted as collective modes. Very good. So let's move on with this. There are examples, of course. Ferro-antiferromagnetic fluctuations are soft near spin order. Pneumatic fluctuations are soft near the order by breaks lattice rotation symmetry. Charge density wave fluctuations are soft near their own order. If you loop currents are soft near their own order, etc., etc. But there is a person here. And person tells you, you was here in the morning. You told everyone that about electron phonon superconductors. They were chosen by reason. And the reason is that electron, they were chosen by the reasons that electron-phonon interaction is attractive, but electron-electron interaction, which is screen-Coulomb interaction, is generally repulsive, right? There is nothing to do about this. It's generally repulsive interaction. But there is another gentleman who will say not so fast. Not so fast because it's a long story on its own. I'll try to tell you this story as quickly as possible. You look at screen-Coulomb interaction, and in fact, this gentleman, Landau-Pitaevsky on one side, Kohn-Lattinger after, Anderson with Marel, it's the same time as Landau-Pitaevsky. They said in different ways the same story, that you look at screen-Coulomb interaction and don't think that screen-Coulomb interaction is entirely repulsive. No. At large distances, there are Friedel oscillations related to sharpness of the Fermi surface. And because of Friedel oscillations, which has only power law compared to any exponential tail that you would get for transformation of Coulomb into Yukawa potential, then you had oscillating parts, and oscillating parts occasionally can be negative. So occasionally there can be over-screening, and interaction changes sign. And if you find pairing that is mostly confined to this distance, this distance, this distance, then interaction is effectively attractive for this particular pairing channel. So long story short, what happens when the system becomes close to instability, this oscillation just grows. So we have enhancement of this effect. And because of this, you can try to say that, you can try to find attractive component of overall repulsive interaction. And this was task on their own, but short story is that yes, you get most likely non-S-wave superconductivity out of this. For example, P-wave pairing by ferromagnetic fluctuations, D-wave pairing by antiferromagnetic fluctuations, S plus minus, a sneak-tight story, by pairing by stripe magnetic fluctuations. So you find a particular channel in which interaction is attractive. In other channels, it still will be repulsive. And this is nothing but extension of the story that there are some occasional regions where interaction is over screen and change sign. Once you take this into consideration and work and write down gap equation, etc., you get pretty much the same problem as with the electron phonon case. You get the same dynamical interaction between fermions, and you have pairing produced by this effective dynamical interaction, which means that you have dynamical pairing, solve dynamical pairing problem. And there is a difference. There is a difference between what I told you now and what I told you this morning. Namely, this difference is there is only one velocity in the problem. There is no such thing as fast electrons and slow phonons. All quasi-particles, including collective excitation, they all have only one velocity, Fermi velocity.
How come take, for example, plasmons in 2 dimensions, the square root dispersion, what velocity we are talking about?
What I mean is that yes, plasmons will be, but still everything is. If you look at scales, I guess the relevant scale is still set by Fermi energy. There is nothing else.
Take
Yeah.
one-dimensional systems. The velocity of plasmons is normalized by the interaction, and the stronger the larger is the interaction, right?
Yeah, sure.
So they can be pretty much different from the Fermi velocity in contrast to phenols.
What I mean is, I know what you're talking about. I just don't want to go into shouting much with everything. Yes. No. What I mean is this. Take zero sound. I put it this way. Zero sound velocity is essentially Fermi velocity, right? You can go to strong coupling with zero sound. Yes, velocity will be normalized from Fermi velocity by strong coupling effects. And it can be different from Fermi velocity. But it's not like you start with a system which is prepared to have velocity parametrically different from Fermi velocity, even at weak coupling. You still need strong coupling effect to see these renormalizations. That's what I mean.
That's true.
Yeah, good. Right. So, let me continue. At the first glance, this means that you cannot treat bosons as slow compared to fermions, just one velocity. However, it turns out, and this was important for us in the Lashberg series, but it turns out that all collective excitations of fermions are essentially overdamped excitations. The only difference is zero sound, but zero sound is a special thing. All excitations that become soft and condense at some point, they are all overdamped. And for example, near a nematic transition, you have completely overdamped excitation in the proper particle Hall channel. What it means? It means that on one hand, Landau overdamped excitations are slow mode compared to fermions, simply because fermions are propagating and these excitations are overdamped. On the other hand, it tells you that Landau damping is now part of the story, that you cannot just say forget polarization operator and throw it away from the problem. No, we have to include it. So technically, it means that you need to solve more accurately Eli-Ashberg equations. And this is what I refer to in some sense as Eli-Ashberg computational procedure. Because of course this guy will immediately ask a question about vertex corrections. In order to write Eli-Ashberg theory, you need to neglect vertex corrections. Is there a parameter? The answer is no, there is no parameter. So in fact, this is the theories which don't have a small parameter in this regard. Vertex corrections are of order of 1. They're not large, not small, they are all of order of 1. And then the only issue is, are they big numerically or not? Lowest order corrections are in most cases are of the order of 10 to minus 3. So take it on your own. I think this is pretty good approximation when you can neglect vertex corrections in theories which need to include polarization operator for fermions for sure. Polarization operators for bosons for sure. Okay, there is another difference. And this difference I will try to explore. This difference will work in favor of pairing by collective excitations. And for electron-phonon interaction, fermionic self-energy was divergent. We discussed it at the very beginning of this talk when the bifrequency vanishes. So if you don't want to deal with divergences, you need to keep the bifrequency finite, right? For pairing by collective excitations of fermions are generally strongly momentum dependent. They are peaked either at momentum equal to 0 for nematic ferromagnetic transition or at momentum pi for antiferromagnetic transition, but they're all momentum dependent. And because they are momentum dependent, if you take this guy, neglect m, and then integrate it over the Fermi surface and then basically calculate self-energy. With this guy, you will get self-energy, which is proportional to omega 2/3. It's not Fermi liquid. It's not omega, omega squared, etc. Good, but there's no divergence. So you get what is called non-Fermi liquid at the critical point towards, in this case, nematic ordering, but you don't get divergences. As a result, you have theories which you do calculations without this fear that you are dealing with divergences in the theory. Sure. Generally, look, if you have multi-band system, you have small pockets. Of course, you can play the game with small Fermi velocities because of small pockets. But these are velocities of original fermions, right? Now, suppose you have multi-pocket system and you calculate collective excitations. You still calculate particle-Hall bubbles. This is what gives you all dynamics of your collective excitations. And Fermi velocity is the only scale in the problem. There is no induced other scale. You may at the end of the day get some velocities which are different from Fermi velocity, but it's not like, again, there is no foreign object in the system. Okay, with this, let's do what I want to do. I want to generally consider a case when there is some ordered state, nematic, antiferromagnetic, ferromagnetic, and I take my system, and by changing some parameter, pressure, magnetic field, doping, I want to bring the system towards this critical point when the system becomes ordered. I know that near these points, there are soft bosonic modes. I ask the question, can this soft bosonic mode produce superconductivity? And there are three facts that we know. Fact number one, we just discussed it. If I forget about superconductivity and I ask what happens, what self-energy does to the system, this self-energy, I put this same exponent to third just to be a particular case, produces what is called non-Fermi liquid at this point. And obviously, if I go up in energy, I put temperature, but it can be energy as well, there is some region of non-Fermi liquid behavior that stretches out of this point. On the other hand, if I switch gears and say, well, what about pairing? There is attraction, we discussed this. There is attractive interaction in D-wave, P-wave channel, whatever. So, and then if I forget about non-Fermi liquid, if I just pretend that I solve the system as if the system was a Fermi liquid, I'm pretty guaranteed to get superconductivity around this point. So at this stage, what I'm trying to say is that there are two phenomena. If I take interaction and put it in a particle-Hall channel, it gives rise to non-Fermi liquid. If I turn around, take the same interaction, put it in a particle-particle channel, it will give rise to superconductivity. There is a third fact. Third fact is that there's a tug of war. There is a competition between two effects. And competition can be rephrased mathematically, but easier to say that essentially what happens is that pairing wants to make all fermions coherent. To put them into pairs gives the same phase to all pairs, so it's just like marching band. While non-Fermi liquid is completely opposite to marching band. Each fermion is doing its own stuff. They're all incoherent, etc. So there is a competition between coherence and incoherence. Yes?
When you say incoherence, you mean that incoherence after pairing or incoherence before pairing?
I meant incoherence before pairing because you are asking about competition between two tendencies. What I mean is that generally, if you take incoherent objects, it's very difficult to force them to march in a band. You know that from social studies. Yeah. By this reason, it's not a priori clear on itself that superconductivity will develop, because tendency towards incoherence may win, right? In other words, what I'm trying to say, we have attraction, definitely. We would, if we put everything into Fermi liquid picture, we're guaranteed to get superconductivity. If we compete with non-Fermi liquid, we are not, and we need to study. And this competition is actually, yeah.
I guess for superconductivity, you would get something like a Cooper pair due to the attraction, but in the non-Fermi liquid, what would you get?
I will get,
like not a balanced state?
instead of, no. Instead of propagating excitations, I will get diffusive excitations. Essentially, this is what happens. Fermions will not fly. They will just scatter all the time, right? And generally, it's difficult to force the guys that constantly scatter to combine into marching band. And this is built into Eliashberg theory, because remember what Eliashberg theory is. It's a set of two coupled equations, one for self-energy, measure of incoherence, and other is for the pairing vertex, measure of superconductivity. So why don't we apply Eliashberg theory? We know that vertex corrections are of order of 1, yes. Again, I'm pretty happy with 10 to minus 3 as the number, but technically they're of order of 1. But if forget about this, let's do it. And then let's use advantage. Because we don't have divergences, let's put the system right at the critical point and ask what happens right at the critical point without going around it and trying to make assumptions. You already saw these equations. There's a set of two equations that comes out, one for the pairing vertex, another for self-energy. You can even remember this quantity is called delta, which is prolinear proportional to phi, but also knows about self-energy. What is standing here is the quantity, which is a propagator of collective excitations, which of course I have to integrate along the Fermi surface to get some average of this. And all D wave, P wave is already built into this story. Very good. You may notice that I eliminate frequencies. Internal is small omega, external is large omega, and I eliminate small frequency equal to large frequency. I did it by exactly the same reason I did it for phonons. For all the superconductors, scattering with zero frequency transfer act as impurity, and impurity cancels out from the equation. You can play with this equation and find out that, even without writing this, and find out that this term with two frequencies are equal just cancels out. Very good. What are examples of this chi? What is this function? Well, all examples have been studied, and this is probably the most known examples, and the person who studied it first sits here on the first row. Seriously, it was the first paper. I don't know whether Patrick Lee was doing this in a completely different context. So it was about the same time, I would say. Yeah, but your paper with McDonald and Naik was the first to really seriously look at. Yeah. Look, you take chi, you integrate it over the Fermi surface, which means over one component of Q, you take mass equal to 0. You find that this effective interaction scales as 1 over omega to power of 1/3. It diverges, but if you look what self-energy comes out, you get omega 2/3. You don't get divergent self-energy. You can look at antiferromagnetic fluctuations in 2 dimensions. Again, large number of people sitting in this room who were doing this, and you do the same calculation, and you get exponent minus 1/2. So singular, but with different exponents. You can even do, as number of our colleagues, both from high energy and from condensed matter, doing what happens if you are close to 3 dimensions. You consider anisotropic 3-dimensional system. Well, you get exponent which is very small, close to 0, but still some exponent. If I combined all, you see, all these theories are similar, exponent is different. So here's what I would do. I would just say, well, I'm not interested at this stage in a particular model. I want to consider general trend, competition between non-Fermi liquid and superconductivity. Anyway, this is the title of my talk. So here's what I would do. I would assume that this effective interaction as a function of frequency goes as 1 over omega to some exponent gamma. It's not my name. It was called by Gaby Kotler as gamma model, and takes this gamma as a continuous parameter, and then nail down particular system into this line of different gammas. I want to see whether behavior is the same, and again, I'm trying to answer one particular question: competition between Fermi liquids, between non-Fermi liquid and superconductivity. Very good. Notice, for all these models, we can write down self-energy. It was for particular case of 1 gamma, it was 2/3. Generally, it's 1 minus gamma. And this all is non-Fermi liquid. By the way, quick question, why it's non-Fermi liquid? Yes, but I would expect a little bit different answer. Okay, let me give you my, so go ahead.
Self-energy at 0 frequency should be 0, right?
It's always 0. At 0 frequency, it's always 0. Remember property of a Fermi liquid. Property of a Fermi liquid, defining property of the Fermi liquid is this. You bring fermions closer and closer to the Fermi surface, and they live longer and longer, right? Which means that real part of their green function is much larger than imaginary part of the green function. When you have self-energy, which scales at Matsubara axis as omega to power of something smaller than 1, right? At low frequency, this is larger than the bare omega. Forget about bare omega. G is 1 over sigma. Compare real and imaginary part of this function. You take this guy, convert it on real axis. There's some exponent, e to I pi over 2 gamma, 1 minus gamma. But long story short, both real and imaginary parts scale in the same way. Which means that you never get a situation when the system approaches Fermi level and fermions live longer and longer. This doesn't happen. So you break fundamental principle of Fermi liquid with this. This is why it's called non-Fermi liquid. And power depends on gamma, but I don't care. As long as this power is smaller than 1, we are fine. And I want to work with the systems without divergence. You immediately see that if I take gamma larger than 1, there will be divergence. Let's not talk about this. Let's assume that gamma is smaller than 1. Good. What I want to see, again, I keep repeating, I want to see whether the system becomes superconductor or not. So what I want to do, I want to solve this equation for Tc, which means I want to assume that this guy is finitesimally small, which means I can forget about fine denominator. I can substitute sigma, which is omega to power of 1 minus gamma, and then solve this problem and see whether Tc is finite or not finite. I want to ask a friend. Who is our best friend? Hmm? Yeah, best friend is Raphael, who is the second best friend. Well, there is a second best friend. It's called computer, right?
It's a very old best friend.
I specifically put it as very old. Because for that kind of problem, probably even this guy will solve it. So you ask a best friend computer and put everything in the computer, and computer tells you that, yeah, there is solution. There is a finite temperature, Tc, which goes between some number at small gamma and smaller number at large gamma number. If I look what it is, it's G as the only scale of the problem that I have, just overall coupling, times some function of gamma. Yes, we know this function, even in the proper limits, we know this analytical. It's not a big deal. It's a function, right? So computer tells you superconductivity wins over Fermi liquid. We get pairing instability, right? But I want to take another guy and ask a question. Is it what I told you at the beginning about all these wonderful Cooper logarithms? Or this is something qualitatively different, something totally new, totally non-BCS? And let's check. We already discussed this in the morning. A way to detect Tc analytically is to look at the normal state and then calculate pairing susceptibility. Remember, it means that you put some input bare delta in the problem and then start summing up ladder diagrams to see whether you get divergent susceptibility. Zero at Tc, susceptibility should diverge, meaning that even if you take bare delta infinitesimally small, Your final result will be finite delta. This is your instability. Very good. We know how to do it for BCS superconductor. By the way, BCS is limiting part of this story. You just need to put gamma equal to 0. Self-energy will be omega, right? Put gamma equal to 0, you get BCS. Let's look at this. Well, we know how gap equation looks like. It doesn't depend on frequency in this case, because interaction is now 1 over omega to power of 0, constant. You just get constant attractive interaction. Good. Temperature is there, of course, but it's trivial to solve this equation, right? You don't need anything else. There is 1 over omega. This is standard stuff that leads to Cooper logarithm. So I want to solve this equation in a crazy way. I want to solve it by iterations. Start with phi naught, and then we keep going. And then when I solve this by iterations, you know the story. We get Cooper logarithms. We get first Cooper logarithm, second Cooper logarithm, etc. Omega naught is again upper cutoff in the problem, but the story is not about upper cutoff. The story is that we sum up the standard geometrical series of logs, get the result 1 minus log times minus lambda times log. This is the same story that I told you before. You get superconductivity at the scale that knows about this coupling constant, etc. Right? What I didn't include here, no self-energies. I said just forget about this, because everything is, in principle, I have to write 1 plus lambda divided by lambda. I even didn't do this. But no question, we get essentially Fermi-liquid fermions. They attract each other. We get superconductivity. Cooper logarithm will tell you that this always happens, right? Now I want to do it starting from non-Fermi liquid state and see what we get. Self-energy was omega to power of 1 minus gamma. This is the same equation I had before. It may look a little bit unusual to you, but what I have here, I have 3 components. I have interaction, which is 1 over transfer frequency to power of gamma, right? I pulled out self-energy as omega 1 minus gamma, and this is left over. If I combine this term plus this one, it will be omega plus omega to power of 1 minus gamma. The rescaling factor is g. So it's the same equation that I had before. The product of this term and this term is omega plus self-energy, and this is nothing but interaction. Why I put it like this? Because you look at low frequencies, and you can say, well, this term you don't need. This is just small term, right? Omega to over g to some power of gamma, it's small at small frequencies. So let me look at these 2 terms. One comes with the exponent 1 minus gamma, another comes with the exponent gamma. So what's the total dimension of the kernel? 1, right? Sum them together. And what it means? It means the kernel is marginal. It means that even in this case we get logarithms, right? Which means that if I try to solve it iteratively, starting phi naught, next term will be I put here phi naught. When I integrate over or sum over omega, I get logarithm. Very good. I also get logarithms. Let's see what they give us. We can do everything at finite temperature. Let's do our life easier. Let's check whether we get singular susceptibility at 0 temperature. Because let me phrase this. The conventional story is this. You take susceptibility. It diverges at Tc. You may ask, what happens with this susceptibility at temperature lower than Tc? It becomes negative. Simple. So let's check whether it's negative. 0 temperature. I sum up these logs. First log, second log. I just substitute and do exact summation. And here's what I get. Everything is fine, except that there's a factor 1/2 here. Next term will be a factor 1/6. And you find that it's not geometrical series. It's expansion of the exponent. And when I sum all this, you find out that the total result will be phi naught times some function of frequency which never changes sign, which is still positive number. So I divide this phi by phi naught, I get susceptibility. Susceptibility is positive, which means that I did standard calculations. I summed up Cooper logarithms, and I did not get the result that my computer told me. I don't get instability, right? This is where BCS theory completely fails. It doesn't tell you that system is unstable. So we can immediately ask a question. Did our friend betray us? Can be something inside this old machine that still needs to be checked. And the friend answers, no, 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 I'm good. I'm fine. You are doing bad things. Because if you look back here, here is what I want to do. Right. I want to look at this. Where is the coupling constant here? The coupling constant is here, right? G. We said forget about this term. This is such term that gives us just to essentially high frequency cutoff in the problem. This is G in the high frequency cutoff. This G doesn't account for this 1/2 factor. 1/2 factor is just, you can write down log 1 over omega, log square of 1 over omega, you get all these factors. So then you ask a question, what is the effective coupling constant of low energy theory? And you can say, well, this is number, right? This number that you get here. You may say, well, number can be small when gamma close to 1. No, I just wrote it badly. When gamma close to 1, there are singularities, and you get some singularities here in the numerator, so they cancel out everything. So what computer said, don't do what you did. You don't have a right to do what you did. You are not at weak coupling. Well, our answer will be, maybe you are right. So let's look into this. Forget about this high frequency cutoff. I want to look at low frequency part. This is the same equation I showed you before, but without this high frequency part. Put cutoff at G as the integration over omega. It doesn't matter. And then, guys, I want to wake you up a little bit. I have a question for you. Can you solve this equation? Immediately. Sorry? Can you guess what the solution is? Let's see. Kernel, let's do it this way. Kernel is marginal, right? Total power of frequency in the kernel is 1. Gamma plus 1 minus gamma. If the kernel is marginal, solution is what? Power law. Solution is always power law if the kernel is marginal. And look at this, what we had before we talked to this guy computer. We get power law solution by summing up logarithms, right? We get it. So solution is power law. Great. Solution is power law. So why don't I substitute solution in the form of the power law? The rest can be done in minutes. What it means? You substitute omega to some power, substitute it here, do integration, you get 1 over capital omega to the same power of a, because the omega divided by something with dimension 1, right? So only thing we have to do is to compare coefficient on the right-hand side and left-hand side and get this exponent, right? And summation of logs tells you that exponent in their view should be real and equal to 1 minus gamma. The exact value doesn't matter. What matters is that the exponent should be real. This is what Cooper will tell you. Now, the next part is the main statement that I probably have time to make. I'll do it without fanfare, but I thought that maybe this is really important part. You substitute, you do trivial calculations, the result expressed in terms of bunch of gamma functions. It's really trivial. You substitute, you do integration. Mathematical will immediately tell you what the integral is. If you don't want mathematical, you can do it by hand. You can do it by hand, in fact. And it turns out that no, solution is not real. Solution is the sum of 2 complex exponents. And this is the biggest difference with Cooper summation. Cooper summation will never give you this. If you sum up logs, you'll never get this. You solve exactly without summing logarithms, you get exponents. There is an expression for beta, which is complex in terms of gamma functions. Let's forget it. But it's there. What it means? It means, remember, we want to check whether the system is unstable toward superconductivity or not. So we want to check whether susceptibility is conventional, regular, or something weird going with it. And then we find out that the actual solution is the solution in the sum of 2 complex exponents. And sum of 2 complex exponents can be trivially written as cosine of log of frequency. It's just rewriting. X to power of alpha is equal to e to I alpha log x, etc. And this was done by a number of people in various occasions. Some of them are from high energy perspective, some from condensed matter perspective. What it means? It means that now I have a discrepancy between high frequencies and low frequencies. At low frequencies, my solution oscillates. At high frequencies, it's phi naught plus corrections, right? You may notice that that equation has all positive coefficients. There is no negative stuff. So if I do cranking order by order, I get phi naught, I substitute, I get something extra positive, larger than phi naught. Next order, something extra positive, even larger. So on one hand, my susceptibility will go up. On the other hand, it oscillates. I cannot match the two functions, right? There is infinity in between. And this means that my susceptibility is singular. This is how we find instability. Computer was right. There is instability, but it's not Cooper instability. It's not BCS. It's fundamentally not BCS. The rest is we need to introduce finite phi of omega, finite pairing gap in order to kill this discrepancy between low frequencies and high frequencies. And as I already mentioned, this is a pairing mechanism. It goes now in the literature as complex exponent as opposed to Cooper logarithm. So Cooper logarithm is a property of BCS. Complex exponent is property of superconductivity out of non-Fermi liquid. And these are two different mechanisms. This is just to show that, yes, the system developed superconductivity. You start with some initial trial delta, infinitesimally. It's not exactly infinitesimally, but pretty much small. And then cranking out order by order, you find that it goes up, 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 and then saturates at a finite value. It's, again, nice exercise with the computer.
So you start with something slightly below the zero, or
Sorry?
what is the initial part?
Oh, initial part, I just put some trial function. I even don't need to worry about whether it's always positive, or if you put it completely positive, it will end up exactly the same way. So some infinitesimally small function. In fact, Shanshung Zhang, who played with this, played with quite a number of different initial values and always find this kind of solution. Where are these wonderful Cooper logarithms? Can we go back to Cooper logarithms? The answer is yes, we can. This is a separate part of the story, but I think it's really nice to show you what's going on. The problem that I solved was like this. We have one interaction. If I look straight to you, this interaction gives rise to non-Fermi liquid. If I put 90%, if I put 90 degrees aside, this interaction gives rise to pairing. So it was the same interaction. There was no parameter separating between this direction and that direction. Let's now try to play a different game. Let's assume that there are two interactions. One interaction will give rise to non-Fermi liquid, but another interaction, which we just put same one multiplied by a factor, will give rise to pairing. People who like extension to large n, this is what you get when you do extension to matrix large n problem, starting from standard O2 problem, or starting the n equal to 2 problem. But then what happens is that nothing happens with interactions that give rise to non-Fermi liquid. It remains the same. But interactions that give rise to pairing gets multiplied by 1 over n. And if you take n large, it becomes small interaction. And if it's small, then what we said about Cooper pairing should be completely correct. There should be summing up of Cooper logarithms. And we know that it doesn't give you anything, which means that there should be critical n, above which the system should remain in non-Fermi liquid ground state. Below it should become a superconductor. And again, computer can help you here. This is a phase diagram, what you get. You get a phase diagram at 0 temperature as a function of n and this parameter gamma, which tells that for any value of gamma, if you take n large enough, this means that pairing interaction will be small enough, you will go back to normal state. What normal state means? It means that we have real exponents. You can calculate, exponents are real. If you go into the other side, you have complex exponents, and you get a superconducting state. To be honest to you, why for n equal to 1, you are always here with complex exponent? I still don't quite understand. Why the system always wants to get superconducting, while two phenomena are of the same order. They just differ by a number. You see, you need to change n a little bit and you go back to the normal non-Fermi liquid state. But it is as it is. You always get superconductivity, but for this wonderful reason. Very good. Critical when doesn't matter. Nick, how much time do I have, if I have any?
Maybe about 5 minutes.
4 or 5 minutes. Okay. Let's do it in 5 minutes. I want to close the loop. Because what I told you before, in the electron-phonon interaction, if I take situation when the Debye frequency goes to 0, I get some finite TC. In this problems, I also get finite TC. But these problems, I deliberately said they are the problems when I don't have divergences. When there's the electron-phonon problem, I close my eyes on the divergence of the self-energy. Now I want to close my eyes again. I want to say, what if I just look at electron-phonon case? This interaction goes as 1 over omega squared. We saw this, 1 over omega minus omega prime squared. So in our classification of different gammas, this would correspond to gamma equal to 2, larger than 1. So what I want to do, I want to say, aha, if I take the models that I have, which are well justified for gamma smaller than 1, and just extend it to larger gamma. So why don't we try to extend models to larger gamma, and then ask again computer, calculate TC. You find out that this is what you get. You get TC, which is finite. It doesn't happen anything, nothing special at gamma equal to 1. It keep continue. And it saturates eventually at the value coupling over 2 pi. 2 is somewhere here. It gives you 0.18, and now we understand that this 0.18 is. 1 over 2 pi is 0.16. So we're very close to the limit when there's actually number 1 over 2 pi is. So there's saturation here. It's a minimum value that you get, and we're close to it. This means that if I just solve for pairing, I can close my eyes on the divergences and still work with whether I get pairing or not. And there are systems. We ask, do I do it just for only for electron-phonon interaction? In some sense, yes. But if we want to do something more, there is a bunch of systems which goes under the name of Yukawa YK model, SYK model, which is basically dispersionless fermions interacting with Einstein phonons via random Yukawa coupling. And these models can be adjusted by, they're considered treated in large N, when you take large number of fermionic flavors, large number of bosonic flavors, but the ratio of the two flavors is arbitrary number, the one that you can vary. And depending on this number, gamma changes between 0 and 2. You can take any, you get any gamma you want. So this is the way to go from one limit to the other. Very good. I have 2 minutes left, right? So I just want to show you one thing. Remember, we started 2 times today. Strange thing happened. I again get this 0.18. I reproduce this number, great. But again, I have a situation when I have interaction, which is supposed to be attractive only in a tiny window, and then repulsive, and I get a number. Let's try to look into this. Let's generally compare interaction on Matsubara and real axis for generic gamma. We can trivially do it. We take interaction on Matsubara axis that's always attractive. We just convert omega into omega m into minus I omega, and we obtain interaction on the real axis. It's just trivial exercise. This interaction is complex, generally. Any interaction on the real axis is complex interaction. And it has both real and imaginary part. And then you see interesting things, that real part of the interaction, that we normally say this is what distinguishes between repulsion and attraction, changes sign at gamma equal to 1, and at larger gamma becomes repulsive. You may say, well, I still have imaginary part. But this imaginary part vanishes when gamma goes to 2. And this is exactly what we had. We have a strange situation when gamma approaches 2, read it electron-phonon interaction, and you have susceptibility or interaction. This is effective interaction, which on Matsubara axis is fully attractive, on the real axis is almost fully repulsive, right? So let's compare solutions on the 2 axes. And here is what I want to do. I look at Matsubara axis. Fully repulsive and fully attractive interaction. Nothing special. Not boring result. We get a gap which tends to a finite value at 0 frequency and then decreases as frequency goes up. Nothing special, really. Different colors are different gammas. Number change, but besides number, nothing. Regular behavior. Well, we start looking what happens with, forget about this word, sign-preserving solution. I didn't erase it. Conventional solution, nothing else. So you take this solution, and you either can use Padea to convert it to real axis, or you can solve equation for real axis. This is better. You can write down Eliashberg equations on real axis and solve it. And you find out that suddenly your gap starts oscillating on the real axis. This complex gap, interaction is complex, so the gap is complex. And you find out it's the same solution. This and this is the same function. I just converted function from one axis to the other. A regular function on the Matsubara axis becomes wild function on real axis, and not all wild functions are interesting. You can look at this and ask, what about the phase of this gap? This is this is not overall phase. This is frequency-dependent phase. I just write complex solution, delta prime plus I delta double prime, in terms of the phase. And you see what's going on. The first phase starts acquiring 2 pi phase slips. So system develops phase slips. And the answer is, well, the number of phase slips increases as you approach this exponent equal to 2. You see the number goes up, up, up. And then trivial question. It's the last thing I will say, and then I will. If you have completely regular behavior on Matsubara axis, and you have phase slips on real axis, you want to go from one to the other. Can you do it gradually? Nope, you cannot. You cannot just go away from phase slip is phase slip. It's 2 pi change of the phase, right? How can you end phase slips? I'll tell you how can you end. By vortex. So if you have wild behavior on one axis and regular behavior on the other axis, there must be vortices between them. What I mean by vortices is that it's a point where gap function vanishes, and around this point, that's just one example when gap function vanishes. If I make a circle around this function, around this point, sorry, then phase changes by 2 pi. So it's just like regular vortices, only in frequency space instead of real space, dynamical vortices. Well, we can solve gap equation on a complex plane. We can do this. Eliashberg equation can be written for any complex frequency. You can do it starting from imaginary axis or doing equation on real axis and then use Cauchy. But either way, there's a solution. First, completely regular, and then all these red points is where vortices appears. So you start seeing that when phase slips appears on real axis, in a complex plane, you start developing vortices. And the number of vortices becomes larger, 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 and when gamma approaches 2, they form one-dimensional array. So this is really completely unusual superconductivity when you have this array of vortices, and you see it more accurately here. Each red point around this point, this is phase. If I make a circle around this point, phase change by 2 pi. So these are all vortices. Good. And also I see interesting points. This is just log delta. When delta goes to 0, log delta goes to minus infinity. When delta goes to infinity, log delta goes to plus infinity. I cannot get infinity of delta. This will be singularity in the upper half plane. And everything should be regular in the upper half plane for stability. But you see something approaching real axis. And when I look carefully, what happens is that we can solve gap equation everywhere in the complex plane, not necessarily on the upper half plane, everywhere. And what you see, I will finish in 1, 2 phrases. These are vortices. This is what I was talking about. These are vortices in the upper half plane. In the lower half plane, there are anti-vortices, infinity of delta. And when the gamma approaches 2, this interesting situation when on one axis you have purely abstractive interaction and the other you have purely repulsive interaction. This line of vortices approaching real axis. So it's really change of topology that's about to happen. And I'll try to put it the same stuff. This is the line of anti-vortices. Separated from it, there are vortices. These are really vortex-anti-vortex pairs which split. And when this blue line of anti-vortices approaches real axis, it pushes up more and more vortices in the upper half plane. This is why you have more and more vortices in the upper half plane. Long story short, this is really non-trivial behavior with all peculiarities of non-trivial behavior. And I will show you just one example, density of states. This is what you get in a regular superconductor. Yes, it's coming out of non-Fermi liquid, but it still has a true gap. Density of states is peaked at the gap, and then has some oscillating part, this continuum, which has some features. But you go to gamma equal to 2, and your density of states, instead of this continuum, is just a bunch of delta functions, just a bunch of peaks. So it's really totally non-BCS, completely non-BCS superconductivity, where essentially you get pairing, because yes, you have a tiny, tiny range of attraction when omega d goes to 0, but interaction at this tiny, tiny range is singular. And this is how you get superconductivity. So let me stop here, because otherwise I will tell you many more things which probably will be too much to hear. There is a conclusion of this part. This is the most important part. That yes, there is superconductivity coming out of non-Fermi liquid. It's not guaranteed to you. I showed the example of large N when this doesn't happen. So the system, in principle, can remain in non-Fermi liquid state down to 0 temperature. But in most cases, superconductivity develops. But the reasoning is completely different from what we know from textbooks due to Cooper logarithm. There is no such thing as instability due to Cooper logarithm. Instead, it's a completely different phenomena called complex exponent. As the exponent increases, we have discrepancy between attraction on the Matsubara axis and more repulsion on the real axis. As a consequence of this, dynamical vortices pump up into upper half plane, and they're measurable, in fact, because I didn't tell you about this, but each vortex creates a particular number of vorticity of the gap function on the real axis. So in principle, you can measure this in ARPES. And the special model of electron-phonon interaction and vanishing Debye frequency is really an extreme case when the number of vortices is infinite. It means that this is a critical model. It doesn't look like this from perspective of Matsubara axis, but in fact, this is a critical model. We know what happens when you cross, when you go to larger gamma, but this is a story for another hour of talk. Thank you.
Is there a way to predict gamma based on the model? I mean, for electron phonon, you have 2, but is there like some reason for that?
It's 2 simply because there is no momentum dependence, so you just get 1 over omega square. That's it. You ask, is it possible to predict? Yes. If you know microscopic model, take interaction as a function of q and omega, integrate along the Fermi surface, which means integrate over 1 component of q. Whatever power of omega you get, give you exponent gamma. That's it. It's as simple as this.
Great. In the electron phonon problem, if you're thinking of an optical phonon, there will be damping is allowed to appear.
Yes.
It will appear, right?
Uh-huh.
So the gamma equals 2 eventually will have to look like gamma equals 1. In other words, is there like a way that gamma equals 2 looks like gamma equals 2 is always avoided because of damping? Is that correct?
Absolutely, absolutely. I tried to say this, but was probably very quick. So what happens is this. As long as this parameter, lambda e, is small, damping is irrelevant. Once it becomes larger, damping is relevant. How one can approach omega d equal to 0, keeping this parameter small? Take double limit. Double limit. Only I can approach this model only in the double limit. Otherwise, I have to stop.
Right.
But on one hand, I have to stop, and something else happens at even closer to the point where omega d goes to 0. On the other hand, I get Tc, which is a number, right? And so I can study all these vortices already within the range where Tc is finite, delta is finite, delta is stabilized, right? And all I have to do, I can forget about all words I said. I just take this solution and convert it to real axis. You get all this beauty, and then density of states will start producing your bunch of peaks.
Yeah, by the way, thanks for absolutely fantastic talk. I really like them so much. So this oscillation in the pairing perspectivity that you found, it was theoretic beta, basically, but what was in your beta? Is there some easy physics there, like which scale?
Oh, beta is a number, depends on gamma. Let me give you this answer. Remember I showed you the picture with n. Beta is n critical minus n to power of 1/2 with some coefficient.
Comes from the flavors.
Yeah, it's related to, if you take, it's not, you can put it flavored, but if I just take interaction reduced by n and I have critical n, then you can analytically calculate beta close to the point where essentially what happens when n approaches critical point. There are two real solutions. I told you about one that you get by logs. There is another one that you don't get by logs. Both are real. And one physical, one is not. When n approaches n critical, two real solutions merge and convert into two complex solutions. And this is how you get superconductivity.
Because I was searching if there's such a very easy physical explanation, like you showed this example of how repulsive interactions can lead to attractive ones because of the Fermi surface and sharpness of the Fermi surface, and you get rid of it.
Mm-hmm.
So is there equally?
No, I don't think that it's the same because I'm already in a situation. I think it's a different part of the story, because what you said is absolutely right. But I said, let's take this. Let's assume that we already have attractive interaction. In the Fermi liquid, this would be enough. We have attraction, we get superconductivity. But non-Fermi liquid is another obstacle, because it's not about attraction. It's about taking this bunch of completely incoherent fermions and try to really put them into marching bands.
Yes.
And
I didn't mean that there is a connection. I meant it as an analogy of an easy physical explanation. So do you have equally easy but different physical explanation?
you know, I thought about this. Let me try not to rush with the answer. I thought about this. But the problem which I have with any sort of physical explanation is this. As I told and I mentioned this, we get solution for superconductivity. We get complex exponents. But these are numbers. I mean, I change n a little bit. They become real exponents. Why for n equal to 1 they are always complex, I don't know. So I really don't have this explanation that always should be like this. Apparently, I change a model a little bit, and I can stay with non-Fermi liquid ground state. It doesn't have to be a superconductor. This is why I think it's more like competition between two effects of the same order.
Maybe one more question.
I want to go back to the phase diagrams that you showed at the beginning. Now, you don't have to show them. I'm just...
Which one?
It doesn't matter. Really.
Okay, good.
Just pick, you suppress some phase, you have a Fermi liquid line, and then you have a superconducting dome.
Uh-huh.
Now, is there a difference between superconductivity in the Fermi liquid part and the non-Fermi liquid part? And so basically, if we just did it at some value of x and cooled through this superconducting dome and some putative Fermi liquid, temperature TF, which maybe experimentally not a real thing, do you expect a change in the superconducting state?
I'll give you a quick answer, and then if you want, we can discuss it in more detail. The answer is yes. And the answer is yes in this respect. Again, if you are on Matsubara axis, it doesn't matter, really. It's pretty much the same solution in the Fermi liquid and non-Fermi liquid. It doesn't change much. But if you want to do real experiment, which means that you need to, for example, look at photoemission intensity, you look at the peaks of photoemission, you need to be on a real axis. And here you find out that, yes, despite of the fact that gap has a finite value, you go to frequencies larger than the gap, and you don't get a behavior associated with the continuum. Even in simple ARPEs, you find out that there are excitations which are confined to the gap value. They're just like bound state for any gamma. Then there is a bunch for gamma equal to 2 is a special case, but even if you are at smaller gamma, when the whole story about collective excitation